Abordarse muy bien, por favor. So this is in English today. So very welcome to our KIT Alumni Virtual Coronactivity. This time we need two friends, let's say. I could say Tobias, because I know him, so I don't know how many years ago. And he and Stephan here are going to present the next talk. This is multidisciplinary data acquisition as the key for globally applicable water resource management. As I see, this is divided into two parts. Part one is Stephan here. Stephan, I cannot see you in the gallery. Here, no.
Okay.
Please, Stephan, thank you.
Okay, so thank you for the introduction. I'm still working at KIT at the Department of Water and River Basin Management, and we had the coordination in this MUDA WRM project funded by the BMBF in Germany. It was quite a large consortium. I will come to this later. And my part today will only be about the sediment assessment, but not any sediment assessment. So the major topic of this project was reservoir management, drinking water reservoirs in Germany and in Brazil. So I would like to start shortly with an introduction, explaining a little bit about the overall project idea, and then Tobias and me, we will just take
¿Soy yo o lo perdimos a Stephan?
Sí, yo también.
Se quedó pegado.
Yo también lo perdí.
Okay.
No se escucha.
No.
As you can see here on the right side image, which was one of our first.
Sorry, but we lost you for a minute, more or less.
Ah, okay. Should I go?
You start with this slide again, please, Stephan.
Okay, sorry. So you can see up here our partners from the consortium of this international project, which were a couple of industry partners from Germany, like EFTAS or 52 North, federal or authority partners like the Wupperverband, which is an operator of the water reservoirs, and different universities. And those partners were countered in Brazil more or less one-to-one, let's say, including the UFDR with Tobias and other professors involved. So the idea of this project was, or the overall question was, how can we improve the water management or the management of water quality in drinking water reservoirs? And we would like to come up with ideas or with results which are able to be transferred to other reservoirs around the world. And I will make this rather short now. So we divided this entire holistic approach in the catchment part and in the reservoir part. So the catchment part was a lot about flux modeling. It was about remote sensing applications and so on. We can discuss this maybe later, but today we will focus, Tobias and me, we will focus on the reservoir processes, and I will only talk about the siltation, the accumulation of sediments inside the reservoir. So on the right side is our group, which was roughly 60 technicians, researchers, professors from Germany, from Brazil, and even some other places. 17 PhD students were involved, so it was quite a large project. Okay, why do we actually work, or why do we investigate reservoirs at all? They are highly important structures. Nearly in every country around the world they are present. We have up to 1 million reservoirs around the world, and more than 100,000 larger reservoirs, which means more than 50 meters of dam height, and they produce 20% of the electric energy demand around the world and roughly 30% of irrigation water. Especially in countries where the rainfall is very little or very low or even unevenly distributed, reservoirs play a really, really important role also in the supply of drinking water. This is also the case in Curitiba, why this was one of our study areas. What reservoirs do to the environment is, besides providing all those benefits and useful purposes to humankind, they actually interrupt the continuous flow of rivers. As we build a dam, sediment which is normally transported along those rivers is accumulated, is retained in front of or upstream of the dam where the river is turned into a lake. The same accounts for nutrients, and they may actually threaten the water quality since they accumulate in those reservoirs over long time periods. And there are further consequences like the burying of for the barrier of migrating species like fish, for instance, which might get extinct, but this is not the topic of was not the topic of our investigation. So the motivation why to focus in this case, especially on the sediments, this was one of the large parts from our department. So they accumulate in the reservoir, and first of all, this will lead to a reduction of the volume of those reservoirs. So the capacity the operator can use for electric generation or for drinking water supply is decreasing over time. And sometimes there's so much sediment inside the reservoir that even the intake facilities or the base drains or technical parts of the reservoirs are obstructed, and then it becomes complicated or, let's say, really dangerous. So we have the eutrophication effect, which is accelerated normally over time in most of the reservoirs, and which is also an important research area with the greenhouse gas emissions from those reservoirs, where all the organic material is degraded without oxygen and becomes methane or N2O, and then takes quite a large share actually in climate change nowadays. Okay, so we have a problem that we don't know. Most operators actually don't know how much sediment is already stored, how much sediment is accumulated in the reservoir. And what we wanted to do is we wanted to develop a guideline or a clear technique how we can assess this in the cheapest and the most precise way. So what we did is, because there are many technologies available, especially echo sounding technologies, which means you use sound waves from the water surface to the bottom and back, and this time is measured, so you get the bathymetry, the depth distribution, and some of those echo sounders are able to penetrate with their sound wave into the sediment and measure the thickness of the sediment. In many reservoirs where we have gas, free gas in the sediment, from like this methane, for instance, the acoustic approach does not work, and the numbers produced for the operators are really wrong. So the filtration rate becomes wrong, and therefore the lifetime, the calculated lifetime of those reservoirs is also too high or too low, which can have crucial impact on the management. So what we did, we used different techniques, like a free fall penetrometer, which you can see here on the right side, or basically in the middle. It's like a huge dart. You let it fall into the sediment. I will explain later in detail. And then you can measure the thickness of the sediment. Or you can take sediment cores. Also, there you retrieve material to take it to the laboratory and know a lot more about the composition of the sediment, grain size distribution, and so on. You can just take this sediment dredge down here. It's the simplest way actually to take samples, or you can use more sophisticated acoustic methods with the disadvantages I just explained a little bit. So we did the bathymetry, which means we measured the surface of the lake bottom over the entire reservoir in very high resolution. And from this, we calculated the operator's volume, which is very interesting and useful for the operators. And in many reservoirs, this knowledge is actually not available. So if you do this measurement in every 2 years, every 5 years, which is the monitoring regularity in many countries, then you can differentiate between the volumes over time, and you can calculate the siltation rate from that. But in many countries, this is not being done. So we need other ways to assess how much sediment is inside the reservoir. And in Passauna Reservoir, close to Curitiba, this was the case. There was no precise measurement of the lake beds after the impoundment day, so 30 years ago. So we had no way to do this differentiation. And the operator is using this graph, for instance, to know at which level of the reservoir do I have how much amount of water I can work with, which is especially important if you look at the crisis in Brazil right now. Okay, so what we did then, as one example now, is like using this pre-fall penetrometer. You let it fall to the ground and you get layers of sediment with certain density values, and you can calculate from this. If you have enough points, you can do an interpolation in space. Here you see all those dots giving the thickness of the sediment at certain locations. From that, we did an interpolation, created a map of the sediment thickness, and calculated the actual stock, like the status of the reservoir last year. And from that, divided by the age of the reservoir, we could retrieve how much tons of sediment or cubic meters of sediment are coming into the reservoir every year. This was not only important as an actual statement, it was also valuable in our project as a validation number for all the modeling which happens in the catchment. So the erosion modeling needs a validation, and this is one of the very precise ways to do it. So that's my last slide, and we came up at the end to fill this methodological gap, how to assess the amount of sediment if I have no information from historic data, and I have gas in the sediment, which is nearly always the case, at least in the subtropics and in the tropics, but also many times in German reservoirs. Then I need a specific guideline or a specific set of methodologies to get a precise number of this siltation. And this is a graph of this guideline here, let's say, or decision tree, how to do this, which will be published hopefully soon. And that's one product of our joint project here. So that was my brief presentation regarding this the assessment of sediment here. If there are any questions, we can discuss later. If you want to know more, there's the MUDAC WRM KIT Edu homepage where you see all other work packages which were related, and Tobias, I think, will present another mosaic piece from
I have a question, may I? Cecilia.
Yeah. Yes.
Stephan,
Yep.
your point is very, very interesting for all the world. What you are studying is a problem everywhere. I didn't understand whether the sediment is compact or you can go through for simply for free fall or a free fall detector. What about the compactness of the accumulated material?
Yes, so that's a good question, and it's not so easy to answer because every location has a different sediment composition.
Mm-hmm.
In many parts, it's very fluffy, it's very soft. We could penetrate, not in Passauna, but in other reservoirs, up to 7 meters of sediment magnitude with this 3/4 penetrometer. It's very heavy. It's like up to, you can change the composition up to 20 kilos, and it's very pointy. So it can penetrate quite a lot of sediment, but of course, at the inflow region, where you have more compact sediment with sand and even sometimes gravel, then it is not able to penetrate a lot. But in that case, the echo sounding technology would actually do a better job.
Yeah. Thank you, thank you.
Okay. May I ask you something, Stephan? My question is a quite different question. I am very interested to know how much money do you need for, let us explain it, 1 year research work? How much money? How expensive are your work?
My personal work?
Yes, how much money do you need? I mean, in order to get money to realize your idea, your project, how much money do you need for it?
You mean to write the proposal, or how
Yeah.
much I cost the department? Well, the proposal writing was it's like something between 3 and 6 months, I would say. If you put it all together, from the draft to the full proposal, with so many partners, we had altogether 8 partners in Germany and internationally even more. So that takes quite some time, yeah.
And then, and the second question related to the first one, it's where do you get the money from?
Well, it was all from the BMBF, or you mean the money for the proposal writing?
I mean, coming from Germany, not from Brazil.
Well, I think Tobias may say a little bit about this. So, of course, our project part was entirely funded by Germany, but the
Yes.
Brazilians had quite a large own share.
And what is the relationship between both help from these two countries?
I think, Tobias, you actually calculated the numbers, right?
Yes.
Actually, the funding from the German ministry was around 3 million euro.
Okay. Yes.
And the funding from several agencies from Brazil, mainly CAPES, was around, let's say, 200,000 euro to put in it. So it's a small share, but we paid essentially stipends for our students.
Okay.
And we got some support from the company to buy a boat and those things, but those boats stay with the company. They don't stay with us directly.
Okay, thank you. Thank you very much.
Erwin, your question?
Stephan, I have a question. Can you hear me?
Yeah, of course.
Yeah, okay. You were the technical question. You were saying at the beginning that it's not that easy to measure the depth. Now we are working on a system of transmitting those data. Just this week, we were in a congress in Paraguay, which is very important to know the level of your river just for navigating. So I'm wondering if that is a problem, or your problem was to know the structure of that deposits, because the normal depth in any ship must have the depth to know not to run against the stones. So is technically is there a problem to measure from the boat, measure your depth, or is your problem was more making a large surface by satellites or so that is not so precise? What was the problem, the technical problem in having, right, the corresponding depth of your...
Measuring the depth is not a technical problem anymore. Yeah? Measuring the depth is just a question of efficiency and the precision nowadays. Okay. If you are plus minus 5 centimeters or plus minus 1 centimeter. So that's a technical issue, but that's very far developed in terms of the bathymetric measurements and satellite positioning and so on. Okay. And movement samples and so on. So that's very far developed. And at the end, it's a question of the money you have available for your equipment, let's say. What is more complicated is the measurement, and this was also our overall question in this working package, is the assessment of the magnitude of the thickness of the sediment, right? Because the sometimes in terms of in space, it might change so fast that one technique which works here gives you totally wrong results 100 meters in a certain direction. So that's the complicated part here, that if you approach this question with one methodology, you might get the number which is very wrong without even knowing. And so you have to have, let's say, quite some pre-knowledge of your water body and the type of sediment you expect to find at certain locations to know which technologies to bring or to apply at a certain location.
Stephan, is that only difficult in water? What about in ice? When you measure the thickness of the ice reservoirs, our water comes from ice crust, or in the Antarctic, where you also try to measure how thick are those, where is the soil and where is your glacier? Is that the same problem, or is only in the liquid water that you would have a problem?
I actually, in ice, I have not much competence, but I would, well, I think also different techniques are applied in ice, more like soil seismics, I would guess. But in water, it's different, the way that we have this change of phases between the water phase and the solid phase, and that has an effect on the velocity of the sound, which is very hard to predict the movement inside the sediment, inside the soil, and that makes the interpretation complicated, especially, and that's always the critical part is the gas. The amount of gas bubbles inside the sediment severely change the velocity of sound in the sediment volume, and that's extremely hard to predict.
Thank you.
Thank you, Stephan. Now we continue with Tobias.
Thank you for the question.
Okay. Good afternoon to everybody. So my name is Ing.Bleninger. Just to show you where I'm located, I'm actually currently in Curitiba in Brazil. So the city of Curitiba is right here, and I stop here the simulation so you can see the drinking water reservoir we're talking about just right beside the city, and we are looking here at that specific region. So to start now the presentation. So I'm currently professor for environmental fluid mechanics at the Federal University of Paraná in Curitiba. And I'm actually a KIT alumni. So I did my undergraduate studies and my PhD at the KIT. And I'm happy also to introduce to you Dr. Liège Bosiackis. She's also a KIT alumni, recently did her PhD as a double degree. And I'm using most of her material of her PhD, which I like to present to you here. So this is actually a picture of the upper part of the reservoir. You can see here at the top, the river inflow. Then we have a bridge, which is creating a constraint in the flow. And actually things are changing this year dramatically, not only because of Corona, but also because we have a severe drought. So we have water cut 2 days a week. We don't have water in our houses because the situation currently looks like that. So this was last year and this is this year. So you can see the whole situation at the moment. This is a drone view from last month, I think a little bit earlier. So again, the river inflow is up there. We have the bridge constraint. And what is interesting now, which is visual, we have high sedimentation patterns in one part, but other parts, you even can see the old road here where no sedimentation occurred. So the questions we actually are interested in were, what are the dominant transport mechanisms for sediment entering such a reservoir? And the second question, how we can measure them, actually knowing that they vary strongly in time and in space. And this is what I wanted to address with you here. So something about the theory. So if we have a river, which is usually colder water, entering a reservoir, which is usually warmer, this river usually is denser than the reservoir water and then spreads at the lower part. So the river temperature has influence on density. So we can have different patterns, either the cold river really going at the lower part. Sometimes if the river is warm, it can go on top, or we can have some split situations when the reservoir is stratified. So how do we measure usually those sediment distributions? We have actually different methods and all of them have been compared. One would be like the image you've seen before by remote sensing using satellite images or drone images. So these are different scales, or even near remote sensing techniques with those cameras similar to those on satellites installed close to the water surface. Conventional methods are using turbidity meters. However, these are point samples. And modern methods to measure the water column sediment distributions are using laser diffraction. All of them are optical methods to differentiate between different concentrations. In addition to that, we actually studied acoustic methods. So this is related to what Stephan showed you previously. So he was looking into the sediment or to the interfaces. We are actually looking on the water column. So those are acoustic echoes, which are reflected at particles, then providing us information not only on velocity, but also particle concentration. So those techniques are actually used in the US already for river cross-section measurements, but we were interested in doing the mapping of sediment concentrations by a moving boat technique. So how does that work? So we did several field campaigns. And if we think about a specific location, we started with a boat choosing a certain location. At the beginning, we did those acoustic measurements, so detecting sediment concentrations over the water column. Furthermore, we took integrated samples, so using that sampler, integrated the whole water column. And in addition, we took samples at 3 locations to obtain the variation of sediment concentration at that location. In the second step, in addition, we used that optical methods also to get the results from those. At a second step, the samples, which are not measured in situ. So the interesting thing is using acoustic and optical methods is that we can get in situ measurements. From the others, from the samples, we need to go to the lab. And there are different methods like settling tubes or filtration methods to obtain sediment concentration. And the third step was to correlate those 2 techniques to see whether we can use acoustic and optical measurements for obtaining sediment distributions. And a nice result you can see here. So that time Liège was going with the boat from the river entry, passing the bridge, and then going further downstream into the reservoir. And you can see here from left, this would be the river entry. The bridge is somewhere here, going down in the deeper parts of the reservoir. So what you can see here in colors is actually suspended sediment concentrations, where we can nicely see that in red, so actually the lower parts here are with high sediment concentration, and at the water surface, the concentrations are low or even not visible. So remote sensing would not work here to determine sediment concentrations, but the acoustic techniques allowed us to map the whole system. So this mapping took us, let's say, 1 hour. So we got an instantaneous image of sediment distributions. These plotted lines here are information on temperature distribution. So you can see here at the beginning, we had a rather uniform temperature distribution, and the sediment actually was mixed in the system, so we couldn't find any. Further on in the reservoir, temperatures are higher at the top than at the bed. So here we could see that actually the sediment-loaded river water is then spreading at the lower part of the reservoir. And further on, we did some modeling initiatives. So if you look here on that little movie, this is actually a 3D numerical modeling, which was applied in the group. And we added a tracer to that model. So we can see here in a dynamic image how this tracer from the river water is spreading actually lower the bed and then is stratifying here at the level with the same density as in the reservoir. And we also detected on the sediments, so doing correlations with Stephan's studies, we see different sediment fractions in those different points, indicating that actually the sediment is being transported at the lower part and then settling in those regions, but also far beyond the inflow within the reservoir. And this is related to the upper part. So the upper animation here shows the temperature distribution. So you can see here normalized, so the effect of temperature variation, which is actually the main driver for having these density currents occurring. So with that, I'd like to close showing you these brief results, but I would like to show here also the success of the lessons learned being in a big international project. So actually, the project didn't finance any student exchange or researcher exchange from the Brazilian side. But from the beginning, we were writing additional proposals and combined all those initiatives together by getting funds from Brazil and additional funds also from Germany, the DAD and others. So that helped a lot to increase the project and to get more international. We actually have 5 double-degree PhDs underway. Within that, 10 international committees for master and PhD students, and 4 research days for professors, which is a very nice outcome of that study. And actually, what is also interesting in being international is that international experts talking to our sanitation company here value the outcomes and not only are academic as very often seen here. So with that, I really like to thank DAD and CAPES for their long-time support. And of course, our network within Unipro projects and NOPA, and the KIT Alumni Network, which is always nice when meeting people and then exchanging with our former university. So with that, I'd like to end, and thank you very much for your attention. I'm open for questions.
Thank you, Tobias. Victor?
Yeah.
Yes, Tobias, can I?
Yes.
Yes. Yes. Tobias. Okay.
Victor,
Luis.
first, please. Primero, Victor.
Okay. Tobias, thank you for your really nice charla, conferencia, and thank you for your answer regarding financial aspect of your project. Then at the last, you mentioned the help of the KIT Alumni Network. I would like to know what kind of help did you get from the KIT Alumni Network?
Actually, yeah, it's a good question. Actually, it's not help with respect to finances or to support, but it's more help to keeping people together, to having a place to exchange ideas. And for our PhD students mainly who went to Germany, for them was very helpful to have contact persons there to find an apartment and those things. Mm-hmm. So we didn't go through the network itself, but we built our own network. Actually, Liège is heading as a president our KIT Alumni Club in Curitiba. We are not as efficient as Carla with meetings, etc. Right. But at least we maintain contacts through email and Facebook to exchange ideas whenever people are moving from Karlsruhe to Curitiba or the other direction.
Mm-hmm. Thank you.
You're welcome.
Thank you, Tobias.
Tobias?
Yes.
Can you hear me?
Yes, well.
I have a little bit of a delay. It's very strange because what I see in my monitor is different from what I'm talking, but okay. Tobias, I'm impressed about the draft you have in Curitiba. So all the measures you could do in the last photo with your nice water, now you can really see what is under the sea level. It's impressive. So exactly, wow. So you're sitting on the mud. So how do you supply now the city with water? Because if that was a reservoir, it seems very bad in the situation of Curitiba now with water for the inhabitants. What is the water problem right now that you have?
It's indeed, it's very severe. So if we look at Google Earth, we can see that situation, but still there's some water in the reservoir. So I only showed that upper part. So there's still some water. Currently, this reservoir is only 30% water left. Mm-hmm. And the other reservoirs are very similar. So we are having 4 here. Since March, we are actually not only in home office, but we have water rationing also. So the company is reducing water demands, and they were able to reduce by 20%. So not allowing car wash or whatever. And in addition, they do water rationing. So we, at the moment, 2 days a week, we don't have water. But things are different here than in Germany. So in Germany, you have these huge water storage tanks from the distribution system, which we go directly into the houses. Here, every house or every building has an own water storage. So in my home, we have 2 small water tanks. So whenever water comes in, they are filled, and then we are left with the water for 2 days. So I recently changed those. So I have 1,000 liter now for 4 people, and which is sufficient to survive for 2 days. But a lot of people in the periphery, actually, they don't have those privileges like myself. So it's really becoming a big problem. So people buy mineral water, they stop having a bath, and it's not raining. So still the average rainfall is below the historical values. And we have, of course, low river levels. Most of energy is coming from reservoirs, so not this one. So soon we will have an energy cut also, because they only have a few thermal power plants. So we quite some preoccupied situation at the moment. They're building new reservoirs, and they try to improve reuse. And actually numbers are already nice. So the average water consumption in Curitiba is around 110 liter per capita. I think it's very close to what it is in Karlsruhe. But I think further improvements can be done, like using rainfall water or water from the washing machines for cleaning, what I actually do also at home.
So you will have to use 2 things, the energy efficiency and water efficiency measurement. And these are coming up now, which everybody was wasting time before. And now you're seeing that this is our thin reserves that we have. So this is pushing us to do the right thing.
Absolutely. It's also all about the catchment itself. So I'm not sure if you know the numbers of average rainfall in Karlsruhe. I think it's around 700 millimeters. In Curitiba, it's 1,400. So we have double of rainfall here on average. However, you can see it's a big city, and the rainfall is usually in the so-called Serra do Mar. So the water goes into the interior. But we have 3 million people consuming a lot of water. So at the moment, and without rainfall, we have those severe problems. And what could be thought of also is doing further improvements in the catchment, so doing reforestation, etc., to keep more water in the system, and eventually explore more groundwater reserves, which is not that used like in Germany.
Just on the last question to you and to Stephan, when you have these reservoirs and you see that they are filled up, there is no other way just to drag them and get the mud out. This is the measurement you have to take, unless you have found something else that you wash them continuously, as maybe you showed that there are flows that just carry your mud away, and the others are piling up, where you have turbulence or have no turbulence, so you have deposits. At the end of the day, you will have to get the mud out and throw it somewhere else. Maybe it's a good soil for fertilizing, I don't know, because it's so much organic matter, as you said, you even have a problem with the formation of methane, means that it's a nice organic reservoir that you have down there.
Yes, actually, one measure, what is very efficient, is to not producing sediment. So really looking at the agriculture here. So to improve agricultural activities, to not having bare soil, which would produce the sediment. A second measure which we are working on, actually Stephan might comment on that. So we have that artificial constraint here of the bridge, which serves like a pre-dam. So this is actually sometimes done. So making artificial pre-dams to accumulate the sediment at places where it's easier to be dredged. But it's a lot of material. So the people are asking, why don't you just go there with the trucks and take it out? But we're talking about thousands of trucks. And to extract that material, it's quite rich in organic material from certain places. but it's a huge and expensive effort. And it wouldn't help a lot to change the volume, actually.
Yeah, the extraction. So in Germany, it really depends also to the legislation in the current country. In Germany, for instance, if you have high organic share in the sediment, it becomes by law you have to deposit it like on a land dumping site for a lot of money. So there's a huge discussion ongoing in that regard, that also the law has to be changed, because the masses in the reservoirs are so large, and there needs to be a natural way to get rid of this. So, and the best way is actually to bring it downstream, because all the sediment in the reservoir is missing downstream of the dam. So the most promising or the most natural idea would be to remobilize the sediment and give it back to the river downstream of the dam, which is complicated if you have very large reservoirs, like for instance in Brazil. And then there are many applications nowadays where you can condition the sediment in situ inside the reservoir, where you put tubes on the bottom of the reservoir, adding oxygen, air, or even chemicals in precise dosage to the sediment, enhancing the growth of the bacteria on the ground, on the lake bottom, and they eat basically the organic share of the sediment, reduce contamination, and then you can easily or easier use the sediment for certain applications outside the reservoir. So there are many, many directions which are developed, but none of them is for free. And that's actually the critical part in all countries, that the authorities are not planning with this cost when they start thinking, or when the construction of the dam was initiated. Those costs are not included in the balance, and that's a huge issue. And all the authorities, they're closing their eyes until the last moment, and that's a huge problem.
Yeah, because to solve that, either you build a new dam downwards, a free one, or you empty the one you have already. So there is no other way around. So if you need the reservoir, because the problem is, if this reservoir, as Tobias showed, is for drinking water, you want to have, of course, as clean as possible and deposit all your mud before. So your water costs, water cleaning costs are lower. So you use the natural sediment. There's no way. If you mix that, the problem is, we see this here in the rivers we have in Chile. When you have too much rain, this is a brown, and so you stop the whole city, because the capacity of the treatment plants are not for such a high concentration of mud. So they have to stop, really to stop the whole city, because it's too muddy when you have turbulence, the rains. So it's one way or another, you have to pay it, either continuously or once every 10 or 20 years. I don't know what to do.
One option I did not mention is also a result of this project is, of course, reforestation and better cultivation in the catchment. So you reduce the amount of sediment coming in the first place. And we calculated if you reforest only the 3%